Hello.
Hello.
Sir, are you back?
Yes.
Yeah. So we will start the session now, second session. Yes,
Okay.
welcome back all the participants. So now we will have another session by Dr. Nirma Sensi sir. So that's on optimization techniques. So we'll have one more brainstorming session for the next 1.5 hours. Welcome you, sir. You
Thank
can take over.
you. Yeah. Thank you. Can you see my slides?
Yes, sir. You
Okay.
can.
Thank you. Yeah. So we basically will be talking about optimization for deep learning. So basically, we'll be doing some simple optimization techniques to begin with, just to look at what are the kind of things we look at in optimization. Okay. So the plan of the talk would be as follows. We'll first introduce some simple optimization problem. Then I will introduce how do I characterize minima. Then what is the relevance of optimization problem to deep learning? Then we will introduce steepest descent method. And after that, we'll talk about some specific thing which is done in steepest descent method or any optimization method called line search, and what is the importance of it, why do we do it, and what are the different variants of this optimization technique which are tried. So that's generally going to be the the plan of the talk. So what's the optimization problem? Is basically you have minimized some f of x over x, and where x is belonging to some set omega. That's the general optimization problem. We will be, however, considering only the unconstrained problem. That means there is no constraint on x, and x can freely take any value. So if there are n-dimensional problem, then this x is free to move anywhere in space of coordinate Rn. Okay. Examples could be, let's say we can say minimize x1 square plus x2 square is a two variable problem. And the other one is more which occurs in deep learning kind of scenario. You can say minimize I equal to 1 to n yi minus f xi then semicolon w, which is basically that means w are the actual parameters and xi is evaluated at each of these points. So we sum the errors as we saw earlier. I mean, we sum the square errors, and these are the kind of some of the problems which are there in the you can say example problems we talk about, right? And one can look at many different type of optimization problems. There are problems known as constraint optimization problems. There are problems known as convex optimization problems. But right now, maybe that will be a topic for some another day. We will today concentrate only on unconstrained problem. Okay. Now, just let's try to understand how do I characterize minimum. So, if you look at this curve, this is a function curve in just to illustrate it's in just one dimension, and I've just drawn the function value versus the parameter curve. And if you look at this is the minimum, absolute minimum of this curve, and that's what is called global minimum. But there is here another fellow which is called local minimum. Now, why it's called local minimum? Let's try to understand that, right? So let's see this. Let's see if I have around this point, if I have a small neighborhood around this point, right? If I have a small neighborhood around this point, in that neighborhood, that point happens to be the minimum, right? and that's the concept of local minimum. So local minimum is something which you can say it is minimum in its neighborhood, right? And how do I define neighborhood? I can define neighborhood in a way in which I can say, okay, a very small, points at a small distance from that. All points which are less than equal to that distance. That's called neighborhood, right? So that's a local minimum. That's a global minimum, right? Similarly, this one we have here as a local maximum. Why not global maximum? Because I can always see that the value are going higher, right? Now, is it possible sometimes that you have a local minimum value which is higher than the local maximum value? Sounds pretty unintuitive. How can a minimum be more than the maximum? But if you look at carefully, let me try to just draw you a curve in which you will see that a local maximum actually can be lower than a local minimum. So let's say this is the kind of sorry, just give me a sec. I'll just correct the curve. So here, this is the local minimum, right? And this is the local maximum. So you have a situation where a local maximum is actually you can actually do a lot better by raising this curve a little bit like that, right? You can okay, let me, I don't think I'm too good in drawing curves, but anyway. So if you have a situation like this, here there is a local minimum and here there is a local maximum. So you see the minimum value actually is more than maximum. So, but this is not the global minimum and maximum, these are all local minimum. So this is how you have to understand that there's a local minimum and a local maximum which can occur. Okay. So how do we formally define a local minimum? So local minimum is, before we get into definition of local minimum, let's okay, the first let's finish off global minimum, which is very easy to define. We can say X star is a global minimum of F. Sorry, I mean the typo, going from Rn to R, not R to Rn. So it's a real valued function going from Rn to R. If f of x is greater than or equal to f of x star for all x. What does it mean? If I take any x and evaluate f of x, then value of f of x star happens to be still not greater than that value. So that means f of x star is the absolute minimum value I can achieve, and such x star is called a global minimum. Now, when is x star is a local minimum? X star is a local minimum of f. Again, I mean, same mistake here also. It should be from Rn to R. If there exists some epsilon greater than 0, such that for all x within epsilon distance of x star, so let's say this is my x star, then if I draw some epsilon ball around it, anytime this is called epsilon ball, and this is what is I put it here. What is the meaning of epsilon ball around x star? That means all the points I collect, which is distance is less than or equal to epsilon, and that's the epsilon ball, right? Now, if I take all the points which are at a distance less than epsilon from x star and call it a ball of radius epsilon at x star, any point in that ball has function value not exceeding f of x star, then f of x star is called a local minimum. And for our purposes, we will assume a function f to be differentiable. Okay. Let's move on. So, as we see, the first derivative, if I want to characterize minima, the first derivative must be 0 at local minimum. And why is that? Why is that? Assuming that the first derivative is not 0. let's say we are talking about just one-dimensional problem, and let's say the first derivative is 2 or positive. What does it mean? If the first derivative is positive, that means the function uh, increases as the value of x increases, right? So that means the function must be something like this, and this is the place I'm sitting here, and the derivative is positive. If the derivative is positive, then if I move opposite direction of derivative, that is the negative direction, I will end up decreasing the function value. So this couldn't have been a local minimum, right? Similarly, if the derivative is negative in one dimension, then the function is decreasing as x progresses. So I am in a situation like this. I'm sitting here, and the derivative is negative. So as I increase x, my function value is decreasing. That means if I actually decrease x, what's going to happen? Sorry, if I increase x, the function value is going to be lower. Hence, this couldn't have been a local minimum, right? Because and if I try to see the points in the vicinity, I cannot find any vicinity where this guy is the lowest. And similar is the case here. I cannot find any neighborhood of this point x star where this point is a minimum. So that's only possible if and of course all of us done maxima minima problems in elementary calculus where we figured out that the first derivative at local minima or even local maxima must be 0. I think the same arguments will hold if you talk about maximum. This is about one dimension. Even in higher dimensions, same thing holds, and that we'll see that once more when we look at look at the methods to do optimization in multi-dimension. Now this holds, as I told you already, is holds for multi-dimensions also, and so what we have concluded is if x star is a local minimum, then this is the way of writing vector gradient where, because if it is a multi-dimension, if it is one dimension, then I can simply write, df dx. But if there are multi-dimensions, then I need to have, multiple of them. So df dou f, dou x1, dou f, dou x2, and so on and so forth up to dou f, dou xn. And this whole thing I can collect as a vector, and that's what is called delta f at x, right? So that's the gradient of f at x star, and at a local minimum x star, the gradient also must be 0. Each of these components must be 0. Okay, so we will use this notation del f to denote the gradient. Occasionally, we will also use g to denote the gradient. Okay, and f will denote the function will denote by f. Okay, so note that if f is going from Rn to R, then g is actually not a real number, but it's a vector of dimension n. Rn is a vector with n components. Okay. Now, is that a sufficient condition? Turns out it is not. Why it is not a sufficient condition? That means if just because the gradient is 0, I can't claim it's a local minimum. Well, we have already seen here in these diagrams, here and here, that if f is if x star is a local minimum, then the gradient must be 0. But the other way around is not true. That means the gradient being 0 is a necessary condition but not sufficient. How do we see? So I have just plotted a graph of x cube here. Okay, and let's look at the derivative of x cube at x equal to 0. So that's 3x square, and evaluated at x equal to 0, that is 0. So although the derivative at this point is 0, but clearly it's not a minimum, because if I draw I take any strip around it, this guy is not the minimum. There are fellows which are below this. There are fellows which are slightly above this. So So that's the reason this is not sufficient. And that is in one dimension, at least it's still a little bit better. But if you look at in higher dimension, you have even bigger problems. So I have, for example, I have plotted here below. If you look at x1 square minus x2 square, and if you evaluate its derivative at 0, 0, let's see first what is the derivative of this. Derivative of this is going to be two components. First component is 2x1. Derivative of f with respect to x1 is 2x1, and derivative of this whole thing with respect to x2 is minus 2x2. So that's the derivative, right? And that at 0, 0 is actually 0. But if you look at the point 0, 0, what you figure out is actually it is a minimum in the x direction, x1 direction, and sorry, I have written the labeled as x and y. Let's read that as x1 and x2. And along the y direction, it seems to be a maximum, right? Because in the y direction, the value is lower here, and then it is going up, and this is the maximum. So that's kind of horse saddle you have seen. That kind of shape it makes, and that's why such points are called saddle points. So saddle points are the ones where the derivative is 0, but it is minimum in direction, it's a maximum in direction. So that's it's definitely not a local minimum, right? Because if I put any neighborhood around it, then the whole neighborhood it is not going to be a maximum or minimum. I'm going to find values which are higher than this. I'm going to find values which are lower than this. Hence, this is either a maxima nor a minima. Okay. If there are any questions or not clear, please keep putting in the chat. I can see there, probably respond. Okay. So I heard something in the chat box. The voice is not clear. Is it okay now?
Yes, sir, it is.
Okay. Okay.
Now
And
it's
yeah, there was a question on saddle point. I hope that's clear, because yes, that's called saddle point, because it's minimum from one direction and maximum from other direction, right? Okay. Let's move ahead. Okay. So what do we do? That del fx will be 0 is not a guarantee for local minima, but however, we actually attempt to, most of the optimization algorithm are attempting to actually solve only this problem and trying to find a point where del fx is 0. And it's mostly okay because we use generally algorithm which constantly decreases the function value. Okay, so mostly you end up in local minima, but there is no theoretical guarantee. It may still get stuck in local maxima or a saddle. How can that happen? Let's see that very simple example. So let's say I started from here, and I took a step and I came to this point. Moment I'm here, this gradient is I'm saying actually I decrease the function value, but I got stuck in the local maximum. Now at this point, the gradient is 0. Because the gradient is, any of the algorithm will fail to make any further progress, and they get stuck here. So you may stuck in a local maxima, or even in a higher dimension in a saddle point, coming from even a higher function value to a lower function value, decreasing the function value all the time, still you may get stuck. But this situation is very infrequent and not so likely to happen. So mostly you will end up, the chances that you will exactly hit the local maximum point is really probability 0 kind of chance. So if you are slightly off, then you will still make progress and go to a either depending on where you go, you can make headway towards this local minima or this local minima. So that's why it's mostly okay to use del fx equal to 0 as a condition to try to meet. So that's all we are trying to meet. Okay. Now in DL, how is pure optimization and optimization in DL, how they are different? Let's just understand that a little bit. And then we will go over the methods to do optimization, right? Now, as we have seen the morning lecture also, if you remember the blue points and the green curve, so basically we were trying to minimize the error over training set, and that is called actually empirical risk. Whereas what we wanted to actually minimize was the actual risk, which was the difference from, let's say, the green curve. How much the green curve is away from red curve. If you recall that is what we wanted to. So, for example, let me see here, let me draw here just for the sake of completeness. Let's say, this is my actual curve from which I should have got the data points, and let's say the blue ones are the data points I got. I error over these blue points, but what I get, I am hoping to, and let's say by reducing that error, I got, let's say, this curve, and what actual risk is, or the actual error is the difference between the green curve and the curve I found. Whereas we end up only optimizing this error. We end up optimizing the error. So we end up optimizing these errors, right? There between the blue and this we found. We end up optimizing that. So that's what I think somehow yeah. So that's called empirical risk. Whereas the actual error between the curve I found and the actual green curve is the real risk. So what I am hoping that when I reduce this empirical risk, my actual risk is also getting reduced. That's the hope I have, and that's not obviously true. And that's why we introduced the concept of test error and trying to figure out through test error how how are we doing, how well we are doing on the unseen data. And that probably is a better judge for the actual getting minimized. Okay. Sometimes in the learning parlance we have surrogate loss functions. That means we actually don't have the actual loss functions because let's say we have a 0-1 classification problem. Then if I have n points, then the loss function may be actually exponential in input space dimension. So we use some log likelihood kind of loss function for 0-1 loss. We will not get into details of that, but that's what we understand is the actual loss function what we use is only to drive towards the correct classification, but not necessarily that itself is the classification. Okay, so and that offers better learning. So and one of the techniques of overfitting in deep learning pipelines, if you research on it, is to stop the optimization algorithm earlier than final convergence, which you will never do in optimization problem meant for deep learning. Let's say you have a chemical process going on, and or you have some kind of cost getting minimized in your real factory cost getting minimized. You want to really find out the minimum cost only, and you don't want to stop this optimization algorithm early, because there the main objective was same as the optimization function. Here we are writing optimization function only to indicate and hope that by minimizing that we will actually get better in our performance. And it's not the real actual the test error is not what we are using to optimize the deep learning networks. So from that point of view, in deep learning or in any machine learning, actually getting to the minimum may not be always important. What is important is our error on test sets are better, or in some way we are through empirical risk we are trying to manage the actual risk, and our aim is to minimize the actual risk, whereas for the optimization problem we give only the empirical risk. Okay. Now this is another higher dimension view of global minima, local minima, point, and some plateau area where it's kind of flattish. Okay. Now what you can see is if you look at a deep learning network, then let's say I give a simple example of a single layer network where this three inputs passes through some let's say three inputs, and it goes to one more layer, and there are these weights, right? There will be 9 weights if it's 3:3, right? Now the W1, if W1, W2, W3, if let's say the optimum values were 2, 1, and 3, then you will figure out that whether it is 2, 1, 3 or 3, 1, 2 or 1, 2, 3, all of them would work because it's just symmetric in the weight space. And hence, if 3 was a minima for a deep learning problem in terms of the weights W1, W3, then so is 1, so is 3, 1, 2, so is 1, 2, 3. Hence, there are multiple local minima. They're never going to be one minimum. But that's not necessarily an issue, but it makes it harder in terms of if there is a problem where there is only one minima, then the optimization problem has a solver has an easy time going towards that. Whereas if there are multiple minimas, then it sometimes gets confused into where it is heading to. Okay, so but still, what we are interested in actually is the function value or error value at the optimizer or the optimum weights. So it may not be necessarily an issue from a deep learning point of view, but it's definitely harder for the optimization problem because optimization solver, because there are multiple of them and you need to go to one of them only. Other problems in deep learning you will find is many areas where the gradient in the plateau area, the gradient kind of starts becoming low, and these low gradient areas again are hard for the optimization methods to make progress. Okay, so many of there are many articles how to control vanishing gradients, etc. You will read in your deep learning literature. Okay. Now we come back to our main optimization problem and try to see as how we can try to optimize a function. So the first method we are going to talk about is called steepest descent method. Now let's try to build up this method, and I think this is one of the most natural method which one can look at. Okay. So what you have is, if you are sitting at a point x, if gradient of fx is 0, then I'm done, because that's what I already claimed, that I am not attempting to actually finding the minimum, but I'm only going to attempt to find a point where gradient is 0. Now, suppose the gradient was not 0, then it is easy to conclude that I am not sitting at a minimum. And if I'm not sitting at a minimum, what we want to do is we want to find a direction D in which I should move so that the f can decrease, right? Well, if f can decrease, that is then I have gone to a lower function value, and by design I want to continue to go to lower function values till I can, right? And once I can't do any more, hopefully I've reached a gradient 0 situation and I've reached the minimum. Okay. Now we want to look at the first order Taylor series expansion of f at a point, let's say in the direction D at alpha away. So alpha times D I add to x. So f of x plus alpha D is going to be f of x plus alpha D transpose del f of some x tilde. Now what is this x tilde? So x tilde will be some point between x and x plus alpha D. So for example, if you have, this is your x and this is the direction D, and you have chosen this point to be x plus alpha D, then some x tilde is some point in between them. Okay. So we don't know which exact point, but some point. And why does that happen? This happened because we have truncated the Taylor series to only one term. If we had added higher order terms, then this would have been still x. Okay. Since we don't want to do that, we want to only truncate to first order. Then this is the situation we have. Now, if I don't move too much from x, then it is fair to assume that x tilde and x will not be too much different from each other, and that will not introduce too much error. Okay. Now, another way, if you find of writing Taylor series, can also be like this. F of x is plus alpha D is also written as equal to f of x plus alpha times D transpose del fx. Sorry, just one thing. Okay. Let me rewrite this part one second. So what I meant was, supposingly instead of x tilde, I want to use here del f x itself. I don't want to use this tilde. Then what is the impact? Then the error is order of alpha square. That is the error we are talking about. So if there is a small alpha, then we will not be adding too much error by just having del fx here, and I can ignore this term for small alpha. Okay, and so it's okay to use even del fx here. So now you can imagine a very simple equation, and we can say that this is in near for a small alpha, this is nearly, instead of equal to, you can say it's nearly equal to fx plus alpha D transpose del fx, and I want to decrease f of x. So in other words, I want to find a D in which f of x plus alpha D for small alpha can give me a value which is lower than f of x, right? As we see in the geometry in the next page, we see that the fastest local descent is in direction D equal to minus del fx. If I move in the minus del fx direction, I will get the fastest decrease locally. Okay. Now, how does that happen? Let's say these are, function contours of constant function values. Let's say this is f of x equal to some c1, and this is f of x equal to c2, where c1 is where your c1 is larger than c2. So as we are moving in this direction, the function is actually decreasing. Okay. Now I am sitting at some point x, and this is a tangent to this constant contour curve, and you have this del fx pointing in this direction. Now, as you can see, this whole cone, anywhere I choose d in this cone, I have chosen just one d. Anywhere I choose any d in this cone, you will find that the function is going to decrease at that point, right? Because it is moving inside. However amount you move inside, the function value is going to decrease. However, the fastest descent seem to be in a direction which is just opposite to del fx, right? This seems to be the direction of fastest descent, and which is minus del f. So you choose your direction to be minus del f, and that's what is called the steepest descent direction. Now, if you are not having, like earlier, as I told you before, if I don't have del fx equal to 0, then I can always find this cone where the direction anywhere in this cone, if I move in that direction, I'll be decreasing the function value. Hence, even for multi-dimensions, the local minimum must satisfy del fx equal to 0. Okay, so that's the geometry behind steepest descent. Now let's try to put the method together. Okay, so what is the algorithm then? Algorithm as it emerges, I set the number of iteration k to 0 initially and initialize to some point x0. And while stopping criteria is not met, some stopping criteria, we'll talk about it. What do? We choose some direction d, which is minus del f of evaluated at xk. So, and that's what we talked about. This is the steepest descent direction in which we want to move, which is minus del f of xk. And then we want to find next xk plus 1, which is xk plus some alpha d, such that f of xk plus 1 is less than f of xk. Right? That's our aim. And then set the iteration counter to 1 higher and keep doing this. Right? That's essentially that's it. That's the steepest descent algorithm. That's all. Nothing more than this. Now, however, this simple thing has two things which are yet unanswered. One is where we will spend the greater time is how to find this alpha. And second is I just wrote very simply while stopping criteria not met. So what is this stopping criteria? These are the only two unknowns. Rest all seems to be fairly simple, right? Okay. So before we get into alpha, step size alpha, let's understand when to stop. That's a relatively simpler question to answer. So we stop when gradient is sufficiently small. So that means what we do is we can keep on calculating the norm of gradient, and when that becomes very small number, I can stop. That's one way the criteria, one criteria is used. Some people also use criteria as giving a maximum number of iterations, and beyond those number of iterations, people stop. There can be even other criteria, but we'll not get into many more variations of that. So I just mentioned to you a couple of them. One is based on the size of gradient, and the other one is just trying to fix some number of iterations. And if you are not happy with the function there, then we can always, increase the number. We can always go to more iterations, right? Okay. So that's how it is, right? Now we talked about we want to decrease the function, right? Now, the critical thing, before we get into more analysis on alpha, the critical thing to understand is is this just trying to decrease the function enough? So let's see this case where I have a kind of function which is x square. So obviously I know minimum is 0 at 0, and what I do is I start at a point x0 equal to 2, and then my iterations are like this. Next iterations are xk plus 1 is 1 plus xk divided by 2. So from 0 I will come to 1.5, and the function value here, which was 4, and here it is 2.25. So obviously I have decreased the function. Now from there I will go to, again, same iteration. I will allow 1 plus 1.5 divided by 2, so I come to 1.25. I obviously decrease the function value. Then I will go to 1.125, so on and so forth. 1.0625, I guess. 1.03125 rest. But we can see that I am never going to go, this sequence will eventually converge to 1. So I will eventually converge to 1, but that is not the minimum value. And while every iteration I have decreased the function value, I have not been able to meet this stopping criteria, right? So this is clearly, this is not good enough. Okay. And what is the problem here? The problem here was, after a point, I was not kind of moving at all. I was moving very, very, very small. And so that's a problem to avoid. We should not have a situation where we move very little. Okay. Now, is that the only problem? And if so, let's see what we can do. If we move sufficiently large, is that good enough? Let's see that. So then we turn to the diagram on the right side. Now all I do is whatever iterates I have here, I just multiply them with a -1 power k sign here. And so my first iterate, if I see from +2, I jump to -1.5. I jump to plus 1.25, then minus 1.125. So if you see this, every time I'm decreasing the function value, and in the x domain, moving also quite a bit. See, this is a large step. Every time I'm taking such a large step. But still, I know that this is going to eventually oscillate between 1 and -1. Nothing else is going to, right? It's going to oscillate between 1 and -1. I still did not go to the optimum, which is 0, right? Now, why did this happen? This happened, again, there is another problem where if I move too much without making, so here I just keep on wandering without making too much progress in the function value. So if I move by a certain amount, I must make commensurate function decrease. Is the another, the next problem. Unless I do that, then I cannot, guarantee that my optimization method will progress, right? Okay. So what do I do with so that means now let's, with this, we are prepared to have some kind of a discussion on, step sizes. So what do? We have, one is fixed step size that may lead to oscillations and divergence if large. So for example, if I even don't even put any kind of thing, and if I see that I'll keep moving by large, then I will end up diverging. So that's one problem. Or if that one is too small, then I can keep making very, very small progress, and then it may take too long if very small. So these are the two problems. And also you may notice that the same step size may not be good for the same function at different points. So what step size? Probably you want to make a very fast progress here, but in this region, you want to make your movement slower. So the same step size also may not fit for the same function at all points, right? All stages of the algorithm. So that's the fixed step size thing. And then one more method is to do exact line search. So what you do is, in this direction, in the direction of alpha d from xk, you find alpha so that in that direction, this function is completely minimized. Whatever is the minimum value of that, you find out, right? So that's called exact line search. So you find alpha to minimize f on the line starting at xk in direction b. Now the problem with this is this may become really too much compute intensive. Okay. Second one is inexact line search. I'm not going to get into details of that. So here we have we find alpha, which guarantees me sufficient movement. Why sufficient movement? So that I don't get trapped into this problem. And it is commensurate decrease in f compared to that whatever movement I've taken, commensurate to that I should have some proportional decrease in the function value. Why that? So that I don't get into this trap, right? So as long as I take care of these two, finding any alpha, it need not be minimum along the direction of xk plus alpha d, but finding any alpha that would suffice, and there are some nice convergence proofs given using this inexact line search for stupid descent method, and you can refer to many of the books have carried this proof. You can look at Fletcher's book on optimization theory also for that. Okay, so that's the step-size discussions. Now, with that, so my preferred approach is here. I replace, this step with the inexact line search. This step I replace with the inexact line search, and then my algorithm is completed. So that's the HT-based descent. Now, in machine learning, however, there is another method which is very, very popular. Gradient descent. Steepest descent is not so popular as stochastic gradient descent. Okay, and this method is let's see what is the origin of this method, how it comes, and why do we have this, right? So this is this method is popular in machine learning, and so we do not want to wait for all the training examples before taking one step. See, what is going to happen is if you use this method, then to calculate this del f, okay, you have to go through each and every example, right? Only then you can calculate. So let's say my parameters, instead of x theta, I'm writing now, instead of x, I'm writing my parameters theta, and instead of error, I'm calling it loss L theta. So L theta is 1 by m, sigma I equal to 1 to m, and summation for small li, I'm calling loss for the ith example. So I sum the loss for each of the examples. That's how I get my total loss. And to calculate the gradient, I have to do del L theta. That will be again, compute each of the individual gradients and take their average, right? So unless I go through each of the examples, I don't have del L theta. And if I don't have del L theta, I can't make progress in the steepest descent algorithm. But if I have, let's say, 1 million examples, then I have to go through each of the 1 million examples before I take even a single step. That may be many times a very, very slow process. So what you want to do is not wait for all the examples. So what can you do? So let's observe, what is del L theta? Del L theta can be seen as average of example gradients del L theta, right? So these small del Li is the example gradient, the contribution to the gradient from each example, right? So this is nothing, del L theta is nothing but average of all such gradients. Now I can treat each of these del L theta as some kind of random gradients, and mean of these random gradients is my actual gradient, right? So each of these fellows are basically representing one random sample of del L theta, and so what I do is I decide to use each of the example del Li theta instead of del L theta itself. Instead of using the overall gradient del capital L theta, I start using each of the individual components just one at a time, and because one at a time, that's nothing but that's just you can say one sample of del L theta. That's why it is called del L theta can be seen one sample of a gradient. That's why it is called stochastic gradient, and hence the name is stochastic gradient descent. Okay. So how does the algorithm fan out then? Let's look at this. SGD algorithm, we fix some learning rate epsilon 0, right? That's just similar to our lambda. And then what do? We initialize parameters to some theta naught, okay? And then we set the k equal to 0, the iteration counter to 0, and we set the epoch to 0. What is epoch? Epoch is one round over all the examples, right? So that's one epoch. So if I have 1 million examples, if I go through each example once, that is one epoch. Then I go second time, then is epoch number 2, so on and so forth, right? So while our stopping criteria is not met, which most of the time in DL they will use the maximum number of epochs you want to allow. What you do is, start of each of epoch, you shuffle the samples, and then in the shuffle domain, do over all the samples. What do? Take one sample at a time. Take one sample in sequence. After shuffling, you take in sequence and compute gradient G at theta k using this sample only. Sorry, not samples, using this sample. And what do? You compute theta k plus 1 as theta k minus some epsilon e, which is a fixed step size here, times g. Okay. You can actually modify this to use any of the step size you want, but typically in deep learning, stochastic gradient descent, that's what they use as a fixed small step size, small fixed step size. Okay. And then set k equal to k plus 1 and do it over, complete over one epoch. Once you have done that, then you set the epoch number increment by 1, and for the next epoch, you can try to update the learning rate epsilon based on whatever strategy you follow. Some of the strategy I have given below. So we can use epsilon e as some 1 minus epsilon times epsilon 0 plus epsilon times e tau, right? So and the value of epsilon can be e by tau up to some tau epochs, and we can do after that we can fix epsilon e after that. Okay, there is a minor error here. This should be in you should read this alpha times epsilon e. So you use that, and so basically you have some initial alpha 0 epsilon 0, and then you keep on modifying that, right? No, I guess it's okay. Epsilon 2 tau also you need to choose. I think, yeah, it's okay. Then after up to some tau epochs, and after tau epochs, what you do is you because then it will gradually keep on going down, and you don't want it to go down too much. So you fix your epsilon e after that, and you need to ensure that sum of all the epsilon e's is infinity. Why is that? That is because so that your entire sample space, whatever your space of theta is there, that is reachable from wherever you are. That is what this condition will guarantee. And then second condition will guarantee that you don't wander off too much. Okay. And how do you plot how do you see the initial learning rate? You should plot some few examples and see the loss for choosing initial learning rate. So what you do is, let's say for the first few things, if you find that for a particular learning rate, the learning is not progressing very slowly, then you probably increase the epsilon a little bit, and you can try with different epsilons, and whatever value you think is giving you good enough decrease and taking good enough step sizes, because both are important. Otherwise, you may get stuck in one place. So you can see that you are not oscillating widely, yet making good strides and making decent progress. That can be your initial epsilon. Okay, and final learning rate can be, let's say, a couple of orders below that. Okay, so that's the SGD algorithm. Then moving on, Another is mini batch algorithm. So there what happens is very similar to SGD, but we choose a batch size B, and whatever we are doing, here for each example here, right? We are doing for these steps, we are doing for each example. There we take B examples at a time and compute the gradient for B examples at one time and take average of those gradients. So we use that. So that's the only difference between mini batch and SGD. So basically, if you put B equal to 1 in mini batch, that is same as SGD. And if you put B equal to M, and that's same as your steepest descent. Because steepest descent takes all the examples in every go, right? So B equal to M corresponds to steepest descent, and B equal to 1 corresponds to stochastic gradient descent. In general, you can use some step size like B equal to 32 or 64 and then go over your set of examples. Okay. In practice, people use this mini batch method. Okay. Then let's talk about quickly talk about cover in the remaining 20 minutes or so I have before we get into question answers. Let's try to cover some of the variants of this method. Okay. So a couple of the problem with SGD is just one sec. Okay, one is SGD does not use the curvature well enough, and also it oscillates in case of curvature, and that it inherits from steepest descent method itself has the same problem also. Okay. Second problem, SGD has its own, which is not so much steepest descent, because you are taking samples, and so each sample represents a noisy gradient. It is not actually the gradient, it is some noisy gradient. Okay. And because of the noise, also SGD can have problems. Okay. And sometimes even if you have small gradients, also causes a problem because you don't make sufficient progress. So what do you do in those cases? All these three situations. One is we can use some kind of averaging over previous gradients also to dampen the oscillation. So just to illustrate the point, what you see here in the left diagram is when you're using individual gradients, you can see that it found this to be the steepest direction, moved in that direction. Then at this point, it found another steepest descent direction, moved in that direction. So you see how much of it ultimately it has to reach here, but it has taken a lot of steps. Now, as opposed to that, let's say so the first step will be same here, but while taking the next step, I use part of this gradient and and the new gradient together. Then I can see that I actually moved in a different direction and makes much faster progress, as you can see in the right diagram, right? So this is the method which is called the momentum method. Okay. So what you do here, you choose a momentum parameter alpha, which like between 0 and 1, but it has to be less than 1. Okay. And we can see first as to how method is used, and then we will see some of the next 3 points what I've written there. Okay. So the first thing is, what you do is what changes we need to SGD if you want to use momentum. So you choose a mini batch and compute your gradient G. Once you have computed your gradient G, you calculate something called velocity. What is the velocity? That means I want to see what previous thing I should be using, right? So that's what you want to do here. Okay. So you already have been storing velocity initially. So what you do is you can use alpha times v. So this v is the previous velocity. You can always start with zero velocity, and alpha times v minus epsilon times the current gradient g. Okay, so instead of moving by simply epsilon g, you are moving now by, see, in the steepest in the SGD, you move by epsilon times g minus epsilon times g. Now there, what we are doing is, whatever was the previous velocity. So I added, I have done epsilon times that. That means I have taken somewhat lesser of the previous step times and then did the minus epsilon g on top of that, right? So that's the momentum. This is the momentum term, and this is the new velocity, and then we have theta equal to theta plus new velocity. So if you look at in this, this would have been the, see, this the when you do this, you okay. So typical value of alpha used is 0.5, 0.9, and 0.99. Okay. Just 1 sec. I need to answer one call. Okay. So yeah. So that's what you do for momentum. Okay. There is and this diagram on the right shows you the the red ones and the black ones are the corresponding steps which are taken. The red ones are the steps taken by the momentum method, and the black ones are by steepest descent method. Sorry, the stochastic gradient method without momentum. So you can see that the wild oscillations of the black ones, this red one is trying to dampen the oscillation a little bit, right? This is how this momentum method works. Okay. There is another variant of momentum which is called Nesterov momentum. So the only difference here is so basically let's first look at in the geometry, and then we can always come back to see the equations. So in the actual the momentum which we have done so far, there is a gradient step, and which is the minus epsilon g, and there is a momentum step which is alpha times v. And the actual step we are taking is the sum of these two steps, right? So that's the actual step. And this is sum using parallelogram vector sum. And the Nesterov momentum, what it does is, it first takes the momentum step, and then it actually calculates the g at this point. Not there the gradient was calculated at that point. No, here the calculation of g happens at this point. Okay, and then take the gradient step of epsilon g. So that's the nature of step. So you can see that what it does is first calculate the interim theta tilde. So this is your theta tilde. This point is your theta tilde, and then calculate g at this point. So what it does is, and compute g at theta tilde, and then that g is used in the final, right? Epsilon alpha v minus epsilon g. Okay, and then the rest of the stuff is same. Okay, so that's the nature of momentum. Okay. So another method is called adaptive learning rate. Okay, as you know, learning progresses, we want to freeze the learning, right? And learning rate is decreased. That's one of the things which I already told you we do, right? Because once we have learned something, we don't want to lose it all by making wild oscillations and huge departures from those points. The problem in the deep learning comes because of that is, as we are aware, that some features in our problems may be infrequent and they do not occur so frequently. Let's say you are learning to translate from English to German. Now you have given lot of examples of English sentences, and maybe there is a word called schizophrenia and or something like that, okay, whatever, or some very odd word, okay, abolishment, I mean, and occurs very infrequently. Now whatever parameters were going to be impacted by this word, now they do not get impacted properly, because by the time that word comes, actually the learning rate has gone way down, and learning rate is virtually not allowing it to move at all, and hence not learn at all. So what you want to do is, you want to based on these features, you want to adapt the learning rate on a parameter basis. So what you want to do is, if some parameters have got already impacts of features, then I want to decrease the learning rate for those parameters. But for parameters which have not learned so far well enough, I don't want to decrease the learning rate for those parameters. So how do I do that? I can always see that in terms of I can calculate I can see that the gradient element wise, and I from there I can make out which components are gone through significant learning and which components have not gone through significant learning. So what I do is, I keep accumulating the square sum of gradients. So what I mean by that is that I maintain a vector where the first term is nothing but for over all iterations sigma gi square. So G0 square. Then the next term is sigma G1 square, so on and so forth. So I maintain the historical gradient element wise, right? And if this number is high, that means I have used quite a bit of learning for this component. And if some number is low, that means I have used very little of it for learning so far, right? So that's why we keep doing this accumulation and do that, right? And the third point we'll talk a little later. And what we do is, again, we choose three parameters: epsilon, theta, and a small delta. Okay, delta is typically, you can say, 10 power minus 7, and I'll tell you why it is important for numerical stability to choose this delta. Then we put a gradient accumulator R. So this is what I am accumulating gradient here. This is R. So at each iteration, what you do is, you choose mini batch and compute G, and then update R as R plus this G, and this G and special this is a pointwise multiplication. So if you do G multiplied by G of the current gradient, then you are going to get still a vector where it is G0 square to GD square, right? So that's so you accumulate. So R is still the same vector what I talked to you about, and it keeps maintaining the same vector. Then you calculate theta, the new theta, which is the new parameters, as old theta minus the epsilon, which is the learning rate, divided by root of delta plus R. Okay. Now the delta 10 to the minus 7 was important, because if R is some gradient components are, let's say, 0, then what do? You basically, for that particular, this is component wise, mind you, this is not when you are doing the ith parameter, this should be taken as Ri. Okay. So this is a component-wise multiplication. So when R is 0 for a particular component, then this delta will come to rescue, and this will not become divided by 0. So that's why for numerical stability you choose a small delta. Okay, and that's it. I mean, so now you can see that the parameter which has not got updated enough, that doesn't decrease as much, and if some R component is high, that means that has been updated enough number of times, then that learning rate automatically goes down as the R is in denominator, right? And that's the method of adaptive learning rate. Now and this is called ADA-grad. All these are very popular methods in TensorFlow, and you have all these available there too. Okay. Now this is one thing is, since you keep on accumulating, this number keeps going up, and that can result in excessive decrease in learning rate. That's one of the problem with this method. Okay, so that's where you go to the next method, which is called RMS prop. It's very let's skip the first line. I mean, let's not worry about it. So yeah. So all it says is ADA-grad does not work well for our DL problems. Okay, so Hinton modified basically ADA-grad by making the gradient accumulation exponentially decaying. So what was happening was, here the R continues to grow, right? So here what we are doing is, now what we from the previous R, let's say I take only 90% of the previous R and add to it the new gradient, right? Or let's say so and 10% I add the new gradient. So 0.1 times the new G square, right? So if I do that, that's the kind of thing Hinton suggested. So the R calculation, if you look at, just contrast it to this, where we are just accumulating gradient. Here what we are doing is, we are doing some rho times R plus 1 minus rho times the new grade, right? And this is called this is the new R, and typically you use epsilon rho equal to 0.9. Rest of the method remains exactly what it was, right? Okay. Now, so one of the things you see here is, all these methods are actually, in principle, similar to steepest descent or stochastic gradient descent, except or even the momentum method can be, whichever way we are using momentum. Along with this also, I can use momentum here also, right? So I can use this along with normal momentum. I can also use this along with Nesterov momentum. I'll not get into details of that, but here, whichever way you are using G here, as epsilon G, instead of using epsilon G, if you use this way of using G, then that's the only modification required for that. So both ADA-grad and RMS prop can be modified also to use momentum. Okay. Then we'll get into the last method. I know it is a little too much, but I think just give a little background so that if you go through the methods, you can actually appreciate the differences between them. So here, this is called adaptive moments, and the momentum terms, what it does is it keeps on adapting, and it does momentum on two, right? So one is, it does a momentum on G as well as this. So if you look at earlier, we were doing a kind of momentum only on G. Here, if you look at that, that's what this ended up doing, right? You're doing that here. And if you look at adaptive, this one, it was doing on G point square, right? So pointwise square of G. So this guy, it maintains 2. So S is rho 1 S, plus 1 minus rho 1 g. So this is kind of a velocity term, you can say. And the second one is what is used for the step size is some rho 2 r plus 1 minus rho 2 g, the square, the pointwise square. So that is from the RMS prop. Okay. Now initially we set S and V to 0, right? Initially we set S and V to S and R to 0. Now because we are setting initially them to 0, the first one I get is only 1 minus rho 1 times G, and that's biased, right? Because the I should have actually got G. In true sense, I'm expecting gradient. So what I do is I correct the bias by so this is called the bias problem, and I correct the bias by taking S cap as S divided by 1 minus rho 1 power t. So for t equal to 1, which is the first iteration, this becomes S divided by 1 minus rho 1. And if you look at here, then this is S was 0. So you got updated S to 1 minus rho 1 times G divided by 1 minus rho 1. So that becomes simply G. And similarly, this will become simply the G square pointwise. So this is how the term is used. And then you can use the theta to be theta minus epsilon times this divided by delta plus this r hat cap. So this is the RMS prop kind of thing, and since you are using S cap, that's like a momentum, right? We are, instead of using plain G, we are using S cap here. So this is some kind of a momentum on a gradient. So this has property of both, and this is very popular in actually machine learning projects today. And deep learning, almost everybody I see they use Adams. Okay, and this is a quick comparison between different kind of methods. So if you look at the iterations over entire data set and how the the training cost is there, then if you look at overall, Adam seem to be having a much better performance compared to Adagrad or this Adagrad. This is the green one. This is RMS prop. The light green is it's another method which I have not covered called delta. And this is the SGD with nested over momentum. And this is this one. The bottom one is the Adams method. Okay. So yeah. So that's the this curve and other things. I think if you look at original Adam paper, which is by Kingma and his colleagues, that gives the details of many more details of this method. Okay. So that's all I have to say. Thank you very much. Open for any questions.
Yeah. Thank you, sir. That was a nice presentation from mind-blowing the presentation by Professor. So any questions? I think you can one or two questions can be said.
So there was one question which we wanted to provide a wrap up. So let me just say briefly, from stupendous descent we moved to SGD because we didn't want to wait for the entire going through entire examples. We went to SGD, and SGD has some other nice properties also, which is outside the scope of today's discussions. But you get into actually it helps you avoid overfitting. Okay. Also, however, SGD has an issue of too much of noise dictating the terms, because each example was trying to dictate the parameter movement. So we went to mini batch approach, And then both SGD and mini batch had a similar issue of not being able to use the curvature so well, and that's also the problem with steep-edge descent also. So to circumvent that to some extent, we wanted to dampen the movement in the next gradient only. So what we did was we used some portion of the previous gradient and called a term called velocity. Then we use momentum or nest error for that. The next method we talked about was, and that's still all these methods so far we talked about, the learning rate was basically the fixed learning rate for all the parameters. And ADAGRAD tried to correct that, saying, some of the features I might not have encountered till late in the training. And if that happens, and if I have kind of, reduced my learning rate too prematurely, I may not be able to learn well enough. So to circumvent that problem, what was done was made the ADAGRAD enabled for us to make learning rate based on each parameter. So each parameter had a different learning rate. Then from there, but one of the problem with the ADAGRAD was that the learning rate, the constant, can drop very, very fast because it continues to accumulate all the gradients, right, all the time. So that denominator will keep on going up, very, very fast, right? So that was the problem with ADAGRAD, which was corrected by RMS prop, which kind of use some kind of decay also in the accumulation of gradient square, okay, pointwise gradient square. And then ADAM method, what it does is it tries to incorporate both the ideas of momentum as well as the adaptive rate into one algorithm. Thank you.
I think there is one more question. Suggest good books for optimization for DL.
Actually, there are a lot of good blogs available for these things, so you can go through them. And also the deep learning book by Bengio have also has the good session on good chapter on optimization.
Yeah, so
I can include some of the references and send you a slide later in the day. Some of the blogs and all I can include in my last slide and send you.
okay. Yeah, that was a nice session, great session by Professor Nirmal Sancheti sir. So we had both the sessions from morning 9:30 to till 1 p.m. So were really mind-boggling, and it was so much of information about the optimization techniques and linear regression were delivered. So hope the audience have enjoyed the session. So I wholeheartedly thank Dr. Nirmal Sancheti sir on behalf of the workshop. Thank you very much, sir, for being with us for both the sessions and having delivered your knowledge for the audience. Thank you, sir.
Thank you for providing me an opportunity. And thanks for attending. Thank you.
Thank you. So, audience, you have one more session at 3 p.m. So please join at 3 o'clock for the last session of today. Thank you very much.